Okay, so this is our key. I'm trying to get this to write. For some reason, it doesn't like to write when there we go, when it's recording. So instead of writing everything down, I'm just going to highlight. So I'm going to say solutions. Try that again. Our blue. So as we look at this, we're just going to go through and look at the solutions, and then I'll do the next one. Solutions are something I can see through that are mixed all the way. So like a gas, like, see, saline. That's about it for solutions here. It looks like I might find some when I get back together. Let's go to colloids. Colloids, whoops, whoa. There we go. Colloids, remember, have a Tyndall effect, and they can reflect lights. They also have some other funky things. So when I'm thinking of colloid, it's not going to fall out. So think of suspension as something that will fall out. A solution is the same throughout, but has very small particles. So I'm looking at a colloid. Tomato soup would probably be a colloid. A dental filling is actually a colloid also. Tap water is a colloid because as you put light through it, it will scatter it. If we look at some others here, fog and jello are colloids. Mayonnaise is a colloid. And that leaves the rest to be suspensions. So let's pick another color here, and hopefully if I wait long enough, it will go with the other color. Nope. There we go. That's pink, by the way. We've got both of these are non-A and water will separate because they are covalent and non-covalent. So sodium bromide and carbon tetra will. Sodium bromide is ionic, carbon tet is covalent. Pentane and water will separate because pentane is covalent and water is ionic or polar covalent. Chocolate milk left to sit will separate. Water, muddy water will separate. Octane and water, again, octane is, anytime you see A and E, you're looking at covalent bound. And mint chocolate chip and ice cream would also be a suspension because if you heat it up, all the chocolate chips will fall to the bottom. So that's really quickly. I didn't rewrite them, but that gives you the idea there. Okay, so again, I'm just going to highlight which of the following would dissolve in water. I'm looking for something that's ionic or that can do hydrogen bonding. Nonane is not. Non-known, sorry, is not. But sodium bromine is. Octane is not. It's covalent. Potassium phosphate is. Now, here's where you get a little bit tricky. You've got to remember. It's not going to let me. That's really funky writing. Let's see if I can pick a different pen. Nag, sag. Okay, if you don't know what that is, go ahead and put it into YouTube, and it will actually bring you up a video on NAGSAG, but basically it's nitrates, acetates, which is C2H3O2 negative. Group 1 metals are always soluble, so NAG is always soluble. Anything that's A is always soluble. So the A in SAG is ammonia, it's always soluble, it's NH4+. Sulfates and group 17 metals, sulfates are SO4, 2-, and group 17 metals are chlorine, fluorine, chlorine, bromine, iodine, have exceptions. Their first exception involves both of them. If they are with PMS, so think of if you're with somebody that's PMSing, they are awful to be around. So that is lead, mercury, and silver. If those are with a sulfate, it's not soluble. Or with group 17, they're not soluble. If the sulfates are with castrober, which is calcium, strontium, or barium, they're not soluble either. So here we have lead with sulfate. So even though it's a polar covalent molecule, slightly ionic, it will not be soluble in water. We have methanol here. Methanol will be soluble in water because, oops, it's not going to let me, here we go. Will be soluble in water because of the OH. The OH there tells me there's going to be hydrogen bonding. And then, of course, the last one, mercury chloride, is a group 17 metal with chlorine. Anytime you have PMS, mercury, lead, or silver with chlorine is not going to dissolve. So when we get to number 3, we're talking about electrolytes. Electrolytes are things that are going to dissolve in water and become a positive and negative. So on electrolytes, we cut out the hydrogen bonding. So if a hydrogen bonds, it's not going to be an electrolyte. But if it is ionic and will follow NAGSAG and split into the ions, then it will be an electrolyte. So that would be things like sodium chloride, lithium hydroxide, ammonium sulfate, potassium chloride, not ethane, which is C2H6, because they are covalently bound, not hydrogen peroxide, it's covalently bound, not silicon dioxide, that's covalently bound. They're close together on the periodic table. If they're close, they're covalent. All right, so arrange each of the in the order of the smallest to the largest particles from colloid to solution to suspension. Solution is always the smallest, so we're going to go 1 on that. It's not going to let me write. Lovely. 1, 2, 3. Suspension is the biggest. Remember, it'll fall out. Finish the phrase. Like dissolves like means that polar substances compounds are soluble in polar solvents, and non-polar are soluble in non-polar substances. Which of the ionic compounds are not soluble in water? So again, we're looking for something that is not going to follow NAGSAG and that is not going to dissolve in water. So be careful of, saw me do that, not, okay? So this is not following NAGSAG. Well, calcium nitrate, that's a nitrate, soluble. Sodium chloride, both group 1 metal and group 17 metal, soluble. Another nitrate, soluble. Ammonium and sulfate, both soluble. Sulfate, soluble, but remember it had exceptions. One of them was castrobare. Barium is one of them. So this is not soluble in water. Then we look at the next one, lead chloride. Wait a minute, PMS, lead was one of those. And it is with group 17 metal, so this one is not soluble. Iron hydroxide is not one of our rules. So because it's not one of our rules, it's probably not soluble. Here we have calcium, and this is another way to write acetate, CH3CO2. So this one is soluble because it's an acetate. And we go to silver chloride. Silver chloride is not soluble. That's one of the exceptions. Okay, so in this next part here, you're using these choices to tell me what would increase or decrease the solubility. So as we're looking at these possibilities here, let's see if they'll let me use a pen. There we go. The solubility of KCl in water. This is a solid, like salt. Think salt in water. What would help dissolve it? Well, to increase the solubility, I would probably increase the temperature. I would increase stirring. I would crush the salt. That would all help increase the solubility. Decreasing the temperature, it walked away again, would not, that would decrease the temperature. Looks like it's going to be mystery here really quickly. If you didn't catch that, go back because it's disappearing. I don't know why. Decreasing would be decreasing the temperature. A and B have to do with pressure, and when I'm working with a solid in water, it has no ability to do anything. That only happens with gases. So think pop when you think gases in water. So if I'm trying to get gas to dissolve in water, I'm going to have to increase the pressure. So this is going to be B, and then this would be A. And then if I decrease the temperature, I can keep the gas in solution. So this would be C. If I increase the temperature, we've got disappearing numbers here again. If I increase the temperature, I would decrease the solubility. And if I stir it, I'm actually going to decrease it, and I can't really crush it. Okay? So, sorry about that. If you've missed those, move back and you'll see those hopefully appearing and disappearing. I don't know what's going on there. All right, so this next one is we've got a solution that's made with this much sodium chloride. We have this much water to make a solution. What is the concentration in weight percent? She's given you right there how to do it. Weight. Which one's weight? The sodium chloride. So we're going to take 7.68 grams, if they will quit disappearing, of sodium chloride. And we're going to divide it by the volume, which is 167.8 milliliters. And then we'll times it by 100 because it's asking for %. When we do that, plug it through our calculator here, we get 7.68 divided by 167.8. Get an answer, times it by 100. We get 4.58. Disappearing numbers again. Percent weight to volume. So, okay, so I'm having enough fun. I'm going to stop this, put this one up. I'm going to try and finish the rest at home on my other computer because this one is not playing nice tonight. So I will try and get that up as fast as I can, but I'm going to go home and use my other computer because disappearing numbers are not fun to play with. Okay? All right. See you on Monday.